This next session is going to be introducing two new research projects that we are going to discuss. The first one is the Edinburgh Decentralization Index, which I'll be joined with by Daniel Woods and Dimitris Karakostas, my colleagues here that we're going to be working on this. And then we're going to discuss the Input-Output Research Hub for blockchain technology, which is being launched and is going to promote interdisciplinary research across the whole university towards pushing the state of the art in blockchain technology. So our first topic, the Edinburgh Decentralization Index, is something that it's a project for which I'm very excited about, and we call it the EDI. And I'll spend the first few minutes just telling you a little bit why this is important. And then I'm going to call my colleagues, Daniel and then Dimitris, to tell you more about this project and how we're going to go about it and why it's actually a very challenging research question. First of all, decentralization is at the heart of this information technology advance. That is blockchain technology. I mean, decentralization is something that characterizes it, it cuts through it, and it's what is being called the real distinguishing factor, what gives it value compared to other ways that we have to organize information technology systems. The thing is that we've been very successful, the computer science community, to launch systems that scale globally, but so far, predominantly all the systems are centralized. So what this talk is going to do is going to tell you a little bit what is decentralization and why it matters, and then we're going to come to challenges and give you a little bit of examples about how this research is going to advance. So I'm going to start with the first, what is it and why does it matters? I think it's good first to ask, in design of systems, how decentralization emerges. So technological decentralization actually can emerge naturally from two competing requirements. First is improving the utilization of available resources and then scaling up. Actually, a fantastic example of decentralization is packet switching, which was developed here in the UK at the National Physical Laboratory by Donald Davis, and it's been a tremendous success in the development of large-scale networks. So packet switching basically is a system which, as you see illustrated in this little animation, the delivery of a certain file is split into packets, which are then routed in this network by local decisions that the nodes take. So the advantage here is that there's no need for central planning. There's no central switching system here that takes the responsibility of delivering the information. Now, taking this a bit further, what was observed early on was that there is another very important property that comes with decentralization, and this is survivability. Even though it was not part of the original vision of ARPANET and later the Internet, this became one of its core principles and essential part of the narrative of what is the Internet. Here's the ARPANET as it looked at its very beginning. So if you think about these properties, centralization versus decentralization is two poles, if you think, that a system can be attracted at any given time. In many cases, the optimal utilization of available resources can be easier if you have complete information about what is going on in the system. So recentralization can occur at any time when information gathering and central decision-making makes sense from an economical perspective. Nevertheless, whenever that happens, fault tolerance and survivability are being hurt, because these are properties that are incongruent with decentralization. So basically, when the system centralizes, a single point of failure emerges, and this can be quite critical. So how to understand these single points of failure? Just imagine about this example, which I'm sure you all know. You take the effort to build a spaceship. The spaceship is as big as a whole planet. It's called the Death Star. It's mighty. The whole galaxy is afraid of it. And it has a single point of failure, a thermal exhaust port, that if a small spaceship actually just put a single missile inside that port, the whole thing explodes. So this is usually how the single points of failures are being understood. Catastrophic failures. However, and that's very important to think about it from the perspective that we're sitting, that decentralization and single points of failures can translate to many different things. It's not just catastrophic failures of that level, but also catastrophic failures for other properties that we care, such as censorship or privacy. These are all important properties of computer systems, that especially those that serve large numbers of people and scale globally, and we do not want any of these properties to have single points of failure. So this is why this is an important topic, and it matters. It matters from the coder perspective, because developing for a decentralized platform will contribute to a public resource, as opposed to just contributing to private interest that benefits only a few people. From a user perspective, using a decentralized app is more resilient to counterparty failures and misbehavior. From a system developer perspective, developing on top of decentralized platforms can be more cost efficient, because you don't have to build aspects of the system, right? They're already there for you. So for example, by launching a decentralized app, you can suddenly reach a wide global audience for your application without having to develop it. And finally, from an investor perspective, decentralization has the potential to give higher transparency. And finally, and quite importantly, from a regulation perspective, in decentralized platforms, regulatory requirements can be automatically enforced. And furthermore, digital tokens that live in these decentralized platforms can actually be treated differently from a regulatory perspective. And the concept of decentralization has been recognized by regulators that are both in the EU, the UK, and the United States as an element that matters from the perspective of how different digital tokens are being treated. So this will bring us to why it's difficult to measure it, how it is difficult to measure it, and what are the challenges to measuring it. And for this, I'm going to ask on the stage my colleague Daniel Woods, who is going to take it from this point. And I'm going to pass him also the clicker. All right, Daniel, here you are.
So I thought first we'd kind of, to understand the challenges here, we can stay in the centralized world. So here we're considering, for instance, a firm who's maybe selling goods and services to consumers, or they're applying for a financial service to a bank. And there's some properties of this firm that are easy to observe. So for instance, branding is something that we as consumers see, it's designed for us to observe. But there are other properties that are emergent and difficult to observe. So one of those is cybersecurity, something that I've worked on. And you can imagine, another one would be, for instance, creditworthiness, so default risk. And you can imagine that there's different companies who are interested in measuring these things. So if you're a bank and a firm is applying for a loan, maybe you want to understand the cybersecurity level, because that has kind of an impact on how likely they are to pay off the loan. So we can look to kind of proprietary solutions in this space to understand why I believe EDI needs to be, the Edinburgh Decentralization Index, housed in an academic institution. So this is some marketing material from a firm who claim to be measuring cybersecurity scores. And it appears to be a very good solution. It seems like the market solves this problem. It provides information, addresses the information asymmetry. Because as you can see, the A-rated firms are much less likely to suffer a breach than the F-rated firms. But I want to kind of bring your attention to two problems with proprietary solutions in this space. The first is simply transparency. So if you go to this company and you try to read how do they generate the score and how do they measure, how do they design this experiment to see if the score is useful in predicting breach outcomes, there's just a lack of transparency. So from reading the document, it seems that whether a firm is breached is both an input to the score and also something they're using to validate whether the score is predictive. So they're potentially failing to separate training data from test data. And these things you just cannot see when there's a proprietary solution writing things in a white paper. So that's why the Edinburgh Decentralization Index will be producing research that we will submit to peer-reviewed journals. And I think the second problem with proprietary solutions in this space is adverse incentives. So one thing that emerged is that alongside providing scoring, what these companies also provide is consulting services to increase the score. So this kind of complicates the independence of the people doing the scoring. Another problem is there's essentially a shakedown. So these scores typically take an IP range of a company and collect kind of showdown-style data and use that to quantify cybersecurity. But what some firms found is that they were scored, and the IP range that they were being scored on wasn't actually controlled by the firm. And the scoring firm basically said, well, if that's your problem, you need to pay us a fee to correct this data in our records. So these are some of the kind of reasons why I believe this Edinburgh Decentralization Index is right to be housed in academia rather than some proprietary firm. But, sorry, there's maybe one difference here. So, as you will kind of rightly say, we're talking about a firm, a centralized firm controlled by a board, a centralized hierarchy. Whereas in the context of blockchain systems, the thing we're interested in studying, how decentralized they are, kind of complicates this model. So I thought perhaps a better case study to look at is measuring income inequality. This is similar to measuring decentralization in a blockchain system because when you're measuring, well, similar and different, and I'll talk about some of those differences and why this is a challenging project, but the similarity I see is the reason we're interested in income inequality is it's a proxy for how power is distributed through society. And similarly, when you're measuring decentralization across these different layers of the blockchain, you're measuring how power is distributed among different actors. So the way this is commonly done for income inequality is the Gini coefficient, which I'm sure people have heard of. And the best way to see how that's calculated, so it's a score between 0 and 1, unless there's negative income, which we're not going to consider, is that you kind of line up along the bottom the cumulative wealth. So let's take halfway. So then on the y-axis would be the cumulative income from half of the people in society, the bottom half. So if there is perfect inequality, you would have the bottom half of society hold 50% of the income. Whereas what we see empirically, of course, is more like this curve here. And what that shows, because it falls below the line of inequality, is that income is unequally distributed across society. So perhaps here, 50% of the population hold just 30% of the income. So there's a metric that quantifies this. As you can imagine, if this area was 0, i.e. this Lorentz curve was exactly along the line of inequality, the Gini coefficient would be 0. If the Lorentz curve came out all the way here, which would mean the richest person in society had all of the income, the score would be 1. But I think what's interesting here is we can ask, and I think this will be one of the biggest challenges with the Edinburgh Decentralization Index, how do we get the data for this? How do they collect the data to score this? And how do they do it in a consistent way that means we can compare inequality across different countries? So we can compare inequality in the US, to China, to Germany, to the UK. And the predominant way of doing this is actually household survey data. So there's statistical bureaus in different countries around the world, and they regularly survey the population, and they collect this self-reported information about how much people earn. And there's been, decades and decades and decades of developing the right way to do that, the right way to do that consistently across countries so we can actually compare statistics across countries. But there is a difference in the Edinburgh Decentralization Index. So what we're trying to do is not ask the people involved in the blockchain system, how much power do you have? How much hashing power do you have? How much coins do you have? Because actually with blockchain technologies, there's a transparency that means we can measure these things directly. So we're no longer relying on self-reported data. We can look directly to the blockchain and quantify some of these things by collecting primary data. And I think, as you can imagine, this creates a number of problems because just like economists are interested in comparing income inequality across many different countries, we are interested in comparing decentralization across many different blockchain systems. They're using different technological solutions. So each time we study a new blockchain system, we need to develop a new parser to collect that data. So this is one of the challenges we're going to have to overcome. And we've begun to do that for a specific layer of kind of blockchain protocols. And I will pass over to my colleague, Dimitris, to talk through some of the initial data related to that.
Thanks, Daniel. So what I'm gonna talk about first is a case study. So let's look at one of these projects. And usually when you look at some blockchain, you look at Bitcoin. Because Bitcoin was the first one, it was the originator of all this whole industry, this whole discipline. And it's the standard to which we compare everything, more or less. So what I like to tell the students here at the university is that a blockchain is a database. It's a unique type of database, so it has this idea of the decentralization. It is unique in that sense. We didn't have that before. And it is unique in the sense that you don't delete data. If everything goes well, data just gets added into the database. You don't delete it, you don't change old data. And the way you do that is you bundle information in blocks, and you link these blocks with what came before. So you create a chain of blocks, in other words. So that means that he who controls the blocks controls the information that gets added into the chain, into the database, and possibly can attack the system if they control enough of the blocks. So if we want to see the systems as decentralized, we would like to see a diversity of people or parties or entities that add the blocks to the chain, right? So let's look at Bitcoin. How does Bitcoin look like? So in 2019, Bitcoin turned 10 years old, in some sense. And the blocks of 2019 looked like that. So this is a distribution of blocks that were produced in Bitcoin in 2019 by addresses, or you can think of it as Bitcoin usernames, Bitcoin pseudonyms. So here you can see that it's somewhat centralized around 7, 8 entities maybe. Entities, again, being pseudonyms, right, being addresses. But the thing is that these systems, there is no enforcement on identity. So there is no control on who can participate, on who creates identities. So someone might control different pseudonyms, just like in Twitter, for example. You might have many usernames. So in reality, what the distribution looks like is something like that. So these are entities, or mining pools, as we call them, which create the blocks. So each of these entities, the leader, the controller of these entities, of these pools, was responsible for organizing the information in blocks, constructing the blocks, and then publishing the information on the database. So you can see here that centralization actually gets a bit worse. So here we have 3 entities controlling a majority of the blocks in 2019. And it gets even worse because some of these pools actually were under the umbrella of the same organization, the same company. So in reality, if you look at legal entities like companies that control the blocks in Bitcoin, the distribution looked like that. So there was one company that had almost 50%, so 40 something percent of all the blocks in that year. So you can see that's not great, right? And let's look at the historical data a little more. So here I have a per month analysis of this shift. So the red line here is the addresses, the pseudonyms, and the blue line is this information about the clusters of addresses, so these pools that control clusters of these pseudonyms. And you can see that there is in some cases, there is a big disparity between the two information, right? And if you look at the information in a little more fine-grained way, here we have what we call the Nakamoto coefficient. So the Nakamoto coefficient is a metric that tells you, or it wants to tell you, how decentralized or centralized block production is. And it's very simple in the sense that the Nakamoto coefficient tells you the minimum number of parties that controls a majority of blocks. So here you can see that the red line is the Nakamoto coefficient of pseudonyms, of addresses, and the blue line is the Nakamoto coefficient of these clusters, of the pools. And you can see in Bitcoin, it ranges between 2 and 4 in terms of legal entities for the months starting from 2018 until this month. So this is one metric, but you can use another metric. So for example, the Gini coefficient that Daniel presented can be used on this distribution as well. There's no restriction on wealth. So for example, if you look at the Gini coefficient of the distribution of blocks across pools or across addresses, you might not be able to see it here, but I can tell you it's about 0.8. And I should say that 1 is the worst. So 1 is the most centralized. So Bitcoin block production, in terms of Gini coefficient, was about 0.8. And finally, in the dotted lines here, show you the percentage of power that, the parties actually controls. These pools actually controlled. So this percentage was about 60-something percent. So 2, 3, maybe 4 entities control about 60% of the block production. So that was Bitcoin. And I'm not sure what you think, but I think it's not that great, especially when decentralization is the principal idea behind these systems. OK, so this was one measurement. So what we did here was we had a couple of metrics, the Nakamoto coefficient, the Gini coefficient. We looked at this part of the system, which was the block production, how information is bundled in blocks and put into the ledger. And we did this analysis, and we found these results. So what we would like to do is to broaden the analysis more, to make it more generic. So this is what the ADI, the Decentralization Index, will try to do. So this is the methodology I will present you in the next 5 minutes or so. So the idea, the high-level idea, is to look at all the layers that form a blockchain, to touch upon all the aspects of the system, and then do an analysis similar to what we did for blocks in Bitcoin, and to find the correct metrics or the relevant metrics that give us a nice picture of what kind of centralization or decentralization we have. So let's look a bit more at what we did so far. So what we did before, in the example I gave you, is we looked at the distribution of blocks, right, of these bundles of information, and how this distribution, how blocks are distributed across some relevant parties. And the parties might be pseudonyms, addresses in the system, or they might be miners or pools, mining pools. And the reason we do that is because, as Aggelos says, if we have a single point of failure, or if the distribution is centralized across a handful or even one party, then problems might come up. So if a small set of parties, if a small set of entities controls a majority, first of all, it is easier to corrupt a small set of entities compared to corrupting or a larger set of parties. And if you do manage to corrupt these parties that control the majority, what you can do is you can do all sorts of interesting things. Some call them attacks. So you can, for example, do a safety attack, which means you change the information that was posted on the blockchain, on the database, that everyone presumed couldn't change. So this is what we call a long-range attack. And also, and this is more sinister because it's not easily identifiable, you could do what we call a liveness attack. In other words, you can censor some information from being put on the ledger. So you could prevent some information from being added into the database. And you don't really want that because, well, that's not what these systems propose. That's not what the systems want to guarantee. Okay, so this is one aspect of these systems. So blocks, the information and so on. But there are other aspects, as I said. So one other is, for example, wealth. I don't know if you know it, but blockchains have to do a lot with money. So they have these tokens, which are native to the system, and you use these tokens to do these kinds of transactions, these payments. You move financial assets between different parties. So what we could do is we could take this idea from before and apply it on tokens. So how are tokens, this new form of money for some, are distributed across relevant parties? And now the relevant parties are different from before. So the relevant parties now might be addresses, pseudonyms, but these now represent investors or users in the system. And again, if we have centralized distribution of tokens, problems might come up. So in some systems, like proof of stake, for example, your security relies on the people that have the tokens being honest. If a majority of tokens is controlled by corrupted parties, then the security cannot be guaranteed. Or even if you don't have that, even if you're in a vanilla setting like Bitcoin, for example, still, these parties that control the majority of tokens might be able to manipulate the price. And if they manipulate the price, the system becomes less usable. And that means that, well, it is harder to actually use the system for its intended purpose. And again, in this aspect, in the tokens aspect, we have the wealth, so the distribution of tokens. But these tokens are financial products, right? They are financial assets. And you can trade on them on traditional markets. So you can sell them, you can buy them, and so on. So now we have a different subcategory in this broad layer, which are the markets, the secondary markets on which you trade these assets. So the relevant resource here would be the liquidity, in other words, the tokens that are up for sale. And the relevant parties now are again different from before. So they are exchanges, the marketplaces, the companies that control the marketplaces, or the trading pairs, so the assets with which these tokens are traded. And again, if this is centralized, if a handful or one exchange controls the majority of the liquidity, it becomes much harder to use the system because, first of all, it becomes harder to get onboarded, to get some tokens, because the exchange might control who is allowed to get some assets. And also, the exchange might also manipulate the prices by doing all sorts of bad things on the marketplace they control. So here, you see a pattern, right? So we see a distribution of some resources that are of interest across some relevant parties. So if we generalize this, what we want to do as a generic methodology is we want to distill all the different layers that form a blockchain. And on each layer, we want to identify the resources that are of interest and the relevant parties that control these resources. And after we have this distribution, we want to find metrics that give us information, that give us an idea of the picture. How centralized or decentralized is this distribution? And these metrics might be quantitative, so they give you a number, for example, which you can use to compare different projects, or they can be qualitative. They can be badges of honor that a project might have, and these badges mean that the project clears some bar. So looking again at the figure, what we have is we have distilled the different layers, and these are the 8 different layers we have identified that are of interest in blockchain systems, and these layers might have subcategories, and they do have subcategories. And in each layer, we have identified the resources and the relevant parties. And the question now is what metrics are of interest? So, following our initial research, what the plan is to produce the methodology for evaluating what decentralization means in these systems. And then we want to develop the framework to evaluate this methodology. We want to write the code that gets the data, analyzes it, and outputs the metrics. And after we do that, what we want to do is we want to release it to the world. We want to make the code open source. Everyone can take a look and identify bugs and inform us on their ideas for metrics or so on. And finally, after we've done that, we want to give a nice visual interface for the regular people to understand what levels of decentralization these projects are at and whether they are of interest for their intended purpose. Thank you.
And I think we have time for 1 or 2 quick questions, but just to connect a little bit the discussion we're having to recent events, just to give you an example of why such a tool such the one that we're discussing here is important. According to some of the reports, I'm sure many of you are following what's happening now with Alameda and FTX. If you look at the supply of the FTT token, which is at the epicenter of these developments in the blockchain space, according to some reports, about 60 or 70% of the supply of that token was held by basically a single entity, Alameda, and clearly such a token would have failed at a decentralization classification as the one that Dimitris was describing. So as you can see, developing such tools and increasing the transparency that users of those systems have in that industry, which in many cases can be quite complex to understand, is an essential element for increasing the robustness and trustworthiness of this technology. So we have time for 1 or 2 quick questions, if there are any. Be happy to take them. Yes, Derek. Do we need a microphone just for the live stream? Yeah.
Yeah, it would have been great to see that graph with the whale concentration as well, just to kind of make a comparison. And what weight would you put on whale controlling of price versus the decentralization of the consensus platform?
Yeah, so I should say that we have already released a paper, so it's public. You can take a look at the website. I guess there should be a link. So there, we actually have some of that information. So we have a table of the Gini coefficient in terms of wealth now, so the distribution of these tokens across different addresses. And we compare different systems there. So we have 5, 10 maybe of these ledgers, and we see how they fare in terms of decentralization of wealth.
And there's probably also a feedback loop, because the people who are doing the consent, like Bitmain, may be one of the biggest whales, right? So there could be a feedback loop between the decentralization of the platform and the control of the token.
Yes, there might be. The problem there is you have to do this kind of de-anonymization. So on the face of it, the ledger doesn't give you this information, the real-world information. So we actually did this de-anonymization for the blocks, and it's kind of sort of easy to do that for blocks. For addresses, for tokens, it might be harder. It's possible, but it might be harder. So this is also something that needs to be done. So when you analyze the data, you have to also do this kind of de-anonymization and see the real-world identities of the parties.
All right. All right. So thank you very much. Thank you very much for your questions. And I think we're ready to go to our next presentation.